Hi people, welcome back to the next lesson on section properties. If you done the ones I told you must do, you'll see they were all, we call them solids or concrete sections. We're now going to apply centroid, second moments of area, section modulus, and radius of gyration calculations to steel sections. Okay. So people, there we have a compound steel section. It's called compound because it's made up of a parallel flash channel, and there's the dimensions. That's its name or nomenclature. This here is a universal beam, and that's its nomenclature. And this is a plate. It's 200 wide by 16 thick. Okay. And of course, we give them names. So because when you go to the steel tables, which is what I've given you before, there's the steel tables. Okay. And I've just marked the ones that I picked at, or marked the ones we're going to work from. So this one is a 406 by 178 by 74. There's a number there, 406 by 178 by, and notice there, this here, these four sections here, okay, they are all 406. Now that distance there, notice it says, if I just make it a bit bigger, if I just look at the top one there, that there says h by b by m. Okay, that h there means it's the distance from the top to the bottom of the flange. Okay, that's h, and b there is 165, so it's 165 wide. So this section is 305 high by 165 wide, and m is the mass per meter. Okay, so that means if I take this section here and I chop off 1 meter of it and I put it on a scale, it will have a mass of 40.3 kilograms. Okay, so in this group of sections here, we've got a 305 by 165 by 40. We've got one of 46 kilograms and one of 44 kilograms per meter. Okay, now people, very important. This here is just its designation or its name. Okay, so this is a 305 by 165 by 40. If I want to find the exact height h there, I go to h, and actually it is 303.8 millimeters deep. That one there is 307.1 millimeters deep, and that one there is 310.9 millimeters deep. So that's its name. So that's just its approximate dimensions. If I want the exact dimensions, I go to the table. So if I take this one at the top here, running along the top, it's exactly 303.8 millimeters deep. It is exactly 165.1 millimeters wide on its flange there. Okay, TW is the thickness of the web. The web is the piece of material lying on the vertical, and it connects the two flanges together. So there's the two flanges and there's the web. So TW is the thickness of the web, is 6.1 millimeters, and TF is the thickness of the flange, and it is 10.2 millimeters. Okay, and R1 there, we call it the fillet radius. There's 1, 2, 3, 4. It is 8.9 millimeters there. Okay, I'm not going to explain everything, and importantly to us, H is important to us, B is important to us, TW, TF, and then the cross-section area of the section is 5.16 times 10 to the power 3 millimeter squared. Can you see that heading there? So I can either record the area as 5.16 times 10 to the power 3 millimeter squared, or I can just say that this section here is 5160 square millimeters. Do you get it? If I multiply that by 1000, it is 5160 millimeters squared. That section there is 5880 millimeters squared, and that section there is 6820 millimeters squared. So you can either write it with the exponential notation, or you can write it fully. I'm generally going to use the full notation. So if I quickly go down to our section here, it's a 406 by 178 by 74. Okay, so the full area for our section is 9530 millimeters squared. So that's what I'm generally going to use. And people, if we keep going across the table, still looking at my first one here, I'm looking at the first section there. Okay, and notice there's the, so the x-axis is the horizontal axis, and the y-axis is the vertical axis, as I've been saying in the previous section there. So Ixx for the first section here is 85.5 times 10 to the power 6 millimeters to the fourth. Did you see that? Okay, and if I can just, no, I can't. Anyway, yeah, so that's the, let me see if I can write here. Can you comment? Anyway, so that there, so this section here has an Ixx value of 85.5 times 10 to the power 6 millimeters to the fourth, and its y value, about the y, and there's the I, is 7.66 times 10 to the power 6 millimeters to the fourth. Okay, and so on and so on. Okay, so as we work through the section, I'm going to refer to the table and pick up the relevant values. But as I said, people, there's our section. I've already marked off. So in our group of sections here, there's 4 of them, but the specific one, notice there, its only different is the mass. It is 74.2 kilograms per meters. There's each H, depth of section, width of section. There's the thickness of the web, thickness of the flange, its cross-section area. There's its Ixx value, and there's its Iyy value. Okay, right, people, let's make a start. Okay, now, and for the channel, if I go to the channel quickly, if I just go down to channel, it's a parallel flange channel. There's it over there. Okay, there's its name, and you will see there as a channel, its name there. Unlike the I section, its name is assessed PFC. It's 260 by 90, and its depth is exactly 260, and its flange thickness, width, is exactly 90. Okay, and there's its web thickness, and there's its flange thickness, and there's its total cross-section area. It is either 4.44 times 10 to the power 3 millimeters squared, but I'm going to use the full value. So its cross-section area, for me, I'm going to record it as 4440 millimeters squared. Okay, and then about its x-axis, its Ixx value is 47.3 times 10 to the power 6 millimeters to the fourth, and about its y-axis, its Ixx, sorry, I'll say that again, its Iyy value is 3.53 times 10 to the power 6 millimeters to the fourth. That Ay there, of that, I'll discuss it as I get to that point there. Okay, people, first question. Refer to the steel compound section shown in figure 1. There's my figure 1. That's my figure 1 over there. We need to calculate the position of the centroid, and I'm specifying from the top left-hand corner of the section. So I'm saying work at Iyy and Ixx for that point down that way there. Right, people, I'm going to draw in some axes over here. Now I'm saying that the X-axis of the whole cross section is going to be sitting somewhere over like so, and that's the X-axis there. It's the X-axis, and that vertical X-axis just happens to be the Y-axis for the whole cross section. So I'm just going to name it. Okay, and of course where they intersect each other there, that is the centroid for the whole cross section. Okay. And then, people, I'm just going to draw in the axes for each of the elements there. So there's my channel, and if I quickly go to my section properties there, I can see there's, okay, now our channel is rotated through 90 degrees. So notice the horizontal axis here is actually the y-axis for the channel, and the vertical axis for the channel is actually the x-axis of the channel. I'm going to draw that in now. So there's its y-axis, and there's its x-axis, and I'm going to name them accordingly. Okay, so there's its y-axis, and there's its axis. And of course, if we go to the section properties for the I section, you'll see from the table there that its x-axis is horizontal and its y-axis is vertical. Okay, and I'm going to draw it in now. So it's sitting somewhere in the middle over there like so. And of course, the y-axis for the I section is sitting on the y-axis of the whole cross section. Did you get that? Okay. So this here is the x-axis of the I section, and this here is also the y-axis of the whole of the I section. Okay. So that's the x and the y-axis of the I section, and that's the y-axis and the x-axis of the channel. Okay, right, I've drawn them here all. So the first question there we need to find is determine the position of the centroid. That means y top, y bottom, x left, x right. Okay, right, so I'm going to say, because I'm working from the top down, I'm going to say y top. And what's the formula? Do you remember the formula? It is the sum of the area of all of them times y over the total cross-section area. Right, I'm going to make that element 1, the channel. I'm going to make that element 2, and I'm going to make the plate element 3. Okay, so channel is 1, I is 2, and that is 3. Right, so A, what's A? A is the area. Now remember when we did the voids, when we did the concrete section, we had to work it out. But now, because we've got steel sections, we've got steel tables, we don't need to work at the area. We go to the tables and we pick out the properties that we want. So I'm going to go to the tables there, and I'm going to go down to my parallel fast channel, which is a 260 by 90, and its cross-section area is 440. Okay, 4440. So it is 4440 multiplied by what's y? Y is the distance from the centroid of the element to the line we taken moment of area is about. So it's the distance from there up to that point there. Okay, do we know what it is? Yes, we do. We go to the tables. Okay, and we see from the tables there the distance from the centroid there to the back of the channel is given by the symbol AY. There's AY over there. And what's AY for the channel? It is 27.4 millimeters. Okay, 27.4 millimeters. So it's 27.4 millimeters plus. Why plus? Because it's the sum of. Alright, area of element number 2, and that's our I section, and it's a 406 by 178 by 74. So I go to the steel tables and I go up to that particular I section there, and there's my I section there. I already marked it out, and its cross section area is 9530. You need to pick out the correct set of values. Okay, so it's 9530 multiplied by y. What's y? Y is the distance from the centroid of the element all the way to the point we've taken moments about. Can we work at that? I think we can. Okay, so the distance from there to the top of the flange of the I section is half the depth of the section plus the thickness of the web of the channel. I'll say that again. The distance y is the distance from there to the top of the flange of the I section. It's half of h for the I section plus the thickness of the web of the channel. So what we need to do, I'm going to go to the I section. There's my I section, and I'm going to go to h. So I'm going to say it's 412.8 divided by 2. So it's 412.8 divided by 2. Okay, and then to that I need to add the thickness of the web of the channel. Okay, there's my channel. So, and then from there I go to the thickness of the web of the channel, which is 8 millimeters. So it's 206.4 plus 8 millimeters, and the distance for The distance y from there to the top there is 214.40 millimeters. Okay, you must make dead sure, yeah, I got that. Okay, you need to work it out yourself. Plus the plate. Okay, now the plate doesn't have its own set of tables. The plate we treat as a rectangle like we always did. So what its area? Its area is 200 times 16. There we go. We treat it as your normal rectangle times. What's y for the plate? Y is the distance. Sorry, let me just quickly draw in. That's the x-axis for the plate. Okay, what's y for the plate? Y is the distance from the centroid of the plate, so it's half of the plate thickness, which is 8, plus the full depth of the eye section, plus the web thickness of the channel. Did you get that? Y for the plate is the distance from the centroid to there is 16/2 plus h of the eye section plus TW of the channel. Right. So let's see. It's 8. I'm going to add it. You stop the video and you work it out yourself. So it's 8 plus, and I need to work at the full height of the eye section. The full height of the eye section is 412.8. 412.8 plus, and of course we need to add in the thickness of the web of the channel, which is 8 millimeters plus 8. So it's 8 plus 412.8 plus 8 is equal to 428.8. Okay, 428.8. So it's 428.8 divided by total area of the cross section. Okay, so 428.8 is 16/2 plus 412.8 of the eye section plus 8 millimeters of the thickness of the web of the channel. Okay, divided by the total cross section area, so it's this plus that plus that, so it's 4440 plus 9530 plus 200 times 16, it is 32.00. Okay, and then you work it out and you stop the video there and you see that you get the same answer like I do. And what did you get? I got a nice round number actually, 206.00 millimeters. Okay, what does it mean? It means this. It means that the distance from there to there, okay, it's called y top, and it's equal to 206. I'm going to write it just like that, for space. Okay, and of course I said there, ooh, and I said there when I did the other lectures that if we know the distance from y top to the x axis and we know the full depth, we can work at y bottom, which is the distance from the x axis to the bottommost fiber of the section, and I'm going to work it out now. Okay, so I'm going to pull my line like so, and then I'm going to draw my arrow from there to there like so, and that there is y bottom. So y bottom. How do we work at the full depth of the section? It's 8 millimeters of the flange of the channel plus 412.8, which is the depth of the eye section, plus 16. Add it all together, take it away from that, will give us y bottom. Okay, do the calculation and check that you get the same answer like I do. And what did you get? I'll say therefore y bottom is equal to, I got 230.80. 230.80 millimeters. Okay, So that's 230.80. Right, people? So if I flick back to my question, 1.1 is finished. Okay. So why I just said from the top left hand corner, you can work from any point, like I said previously, but always take extreme points. That's an extreme point, that's an extreme point, those points are also extreme points, but this section here is wider than the bottom. So it's always safe to take extreme points. You could either work around that point or that point, you get the same answers. Okay. If you work about this point upwards, you would have gotten 230.80 first, and the full depth, take away this, you would have gotten 206 millimeters afterwards. Okay. But whichever way you worked about, you would have gotten either this one or that one, but if you work from the top down, you would have got that one first. If you work from the bottom up, you would have got it first. But the sum of the two must be equal to the full depth of the section of the thickness of the web of the channel plus the depth of the eye section plus 60 millimeters of the plate. Okay, people, that's the first part there. And the next part of the question is work at RXX and RYY of the cross section. Okay. Alright, just give me a second and I'll just clean up here and we can continue with that shortly. Right, people, part B of the section, part B of the question is calculate RXX and YYY, right? And what's the name of the theorem that we use to calculate the second moment of area of a compound section? Yes, you got it, I'm sure, it's the parallel axis theorem, okay? So state it, because I give you a mark for it. So I, big X, and I told you why it must be that last time, okay? Square bracket, and then I, small x, I told you the last time why it must be small, plus a h times squared. Okay, right. I'm going to do section 1 first. I'll put a little 1 over there. Right, what's RXX? It's the second moment of area of the channel. Now, people, are you listening to me? Are you listening to me? Are you listening to me? This way students fall flat when it comes to the channel. I'm going to go to the steel tables and I'm going to flick to the channels. Notice there, I said it before, just now saying it again, the y-axis here, the y-axis of the channel is lying parallel to the x-axis of the whole cross section. So we're not going to work at IXX for the section. We're going to go to the tables and pick out the proper value. But, are you tuning in? But because the y-axis of the channel is lying parallel to the x-axis of the whole cross section, we go to the tables and we pick out its IYY value. Okay, there's my section. So I pick at 3.53 times 10 to the power 6 millimeters to the 4th. Did you get that? It's 3.53 times 10 to the power 6. If you leave that bit out there, it's going to be wrong. Okay? If you leave that exponential bit, it's going to be wrong. Plus the area. What's the area of the channel? It is 440. Yes, for those who remember, 440 times the distance squared. What's h? Are you tuning in? Are you tuning in? Okay. H is the distance from the centroid of the element to the centroid of the whole cross section. Did you get that? H is the distance from the centroid of the element to the centroid of the whole cross section. Can we work at that? Yes, we can, because we just worked at right top. But we need to know the distance from the center to the back there. And you remember what it is? It is AY for the section, and it is 27.4. Okay, so the distance from there to there is Y top. Take away 27.4. So it is 206 minus 27.4. It is equal to 178.60. Do the calculation yourself and check me out. Okay, 178.6. 178.6 squared. Why is it squared? Because the formula said so. Close the square bracket plus. Next one. Element number 2. What's RXX, right? RXX, do we need to work it out? No, we don't need to work it out. We go to the table and we pull out the RXX value for the I section. So I'm going to go to my table. And why do we pull out the RXX value? because its x-axis is parallel to the x-axis of the whole cross section. So I'll go to about x, I go to y, and yippee, it is 274 times 10 to the power 6. So it is 274 times 10 to the power 6 plus the area. What's the area? I think it is 9530 from the previous one. Yes. Times what's h? H is the distance. Are you tuning in? H is the distance from the centroid of the element to the centroid of the whole cross section. Can we work at that? Yes, we can. Because we worked at y. I made a mistake here. I just saw now. My apologies. That there must be y bottom. Silly me. I hope you picked it up. Okay? Y bottom is 230.8 and not y top. Okay, sorry about that, people. Okay? Right, how do we work at h for the I section? How far is it from there to there? From there to the bottom? From there to there is half the depth of the I section plus 16. Take that away from that, and it gives us that. Okay, so I'm going to say, what's the depth of the I section? It is 412.8, and I'm going to divide it by 2. Okay, and to that, I'm going to add the plate thickness there, which is 16. And from that, I'm going to take away y bottom, which is 230.8, and it is equal to 8.4 millimeters. So you can see it's very close, but it's 8.4. But I'm going to leave it red. Okay, 8.4. Close the round bracket plus the plate. And people, the plate we treat as an ordinary rectangle. Okay, so what's our x for the plate? So the question is, what's the second moment of area of a rectangle? It is BD cubed over 12. Yes, what's B? B is 200. Why? Because B is always the side parallel to the axis you take in second moment of area per. So it's 200 times 16 cubed over 12 plus its area. What's the area? It's 200 times 16, so it's 3200. And what's h? H is the distance. I'm going to draw it in here. Let me make it. H is the distance from the centroid of the plate all the way up to the centroid of the whole cross section. Did you get that? H is the distance from the centroid of the element to the centroid of the whole cross section. Can we work it out? Yes, we can. It's y bottom minus 16 over 2. So it's y bottom take away 8. Okay, so it's 230.8 minus 8 is equal to 222.80. So it's 222. I'm going to leave it by that color there. Squared. Why is it squared? Because the formula squared, close the square bracket, is equal to. Right, stop the video there. You do your calculation and you check my answer against your answer. And I'm going to write the answer. You can see it's going to be big numbers. I'm going to write the answer in scientific notation. And what answer did you get? You should have gotten, what did I get? 578. Right, it is 5.787 times 10 to the power 8 millimeters to the fourth. And if you leave the units out, I take up a mark. Okay, it's 5.787 times 10 to the power 8 millimeters to the fourth. Okay, people, so that's the answer there. Okay, so in scientific notation, it is 5.787. If you write it as 5.79, that's fine. But a lot of students write it as 5.787 millimeters to the fourth. They leave this bit out there. That is absolutely wrong. I mean, if you compare 5.787 to 5.787 times 10 to the power 8, 5.787 is a tiny, tiny, tiny number compared to that. Yeah? If you write 5.787, that's wrong. it's 5.787 times 10 to the power 8 millimeters to the fourth. If you leave it a unit, I take up a mark. Okay, so people, that's the IXX value for that particular section over there. Okay, right. Next part of the question, of course, the famous IYY. Okay, let me clean this up here and let's work at IYY for the section. Right, let's bash at IYY. And of course, we're using the famous parallel axis theorem. So there's I big Y, you know that is the case. And that's equal to the sum of, open square bracket, I small y, you know why that's the case, because I explained to you why, plus AH squared using the parallel axis theorem. Right. Element 1. What's I by y? I by y is the second moment of area for the channel. That's element 1. Now, people, very careful. Are you tuning in? Okay, notice there, because the channel has been rotated through 90 degrees, its x axis is now parallel to the y axis of the whole cross section. So when we go to the tables, we must pull out its IXX value. Did you get that? Did you get that? Okay, so we go about IXX and we go to its IXX value, and it is 47.3 times 10 to the power 6. All right, it's 47.3 times 10 to the power 6 plus. What's A? A is the area. What's the area for the channel? It's still 0.0, by the way. It hasn't changed it. Times H. Right? What's H? H is the distance from the centroid of the element to the center of the whole cross section. All right. Have a look there. Have you got your thinking caps on? Are you tuning in? How far is it from the centroid of the channel to the centroid of the y-axis? It falls on the same line. The y-axis of the channel is on the y-axis of the whole cross section, so it is 0. It's 0. So what does it mean? It means that that term there actually just falls away. Plus, I'm doing element number 2. It's IYY for the I section. So what do? I don't work it out. I go to the tables, and I go to the tables where my I section is sitting, and there's my IYY, which is over there, and I come there, and it's 15.5 times 10 to the power 6 millimeters to the fourth. So it's 15.5 times 10 to the power 6 plus its area. It's the area 9530 times. What's H? H is the distance from the centroid of the element to the centroid of the whole cross section. So, how far is the y-axis of the I section to the y-axis of the whole cross section? They fall on the same line. Did you get that? A lot of people gonna give that a distance there, and it is going to be wrong. So this term here, once again, just falls away. You need to be sure to understand that correctly. Okay, I'm doing my last one. What's IYY for the plate? We treat it as a rectangle. So what's the formula for the second moment of area of a rectangle? It is BD cubed over 12. What's B? What's D? B is parallel to the side we're taking second moment of area back. So B is 16 and D is 200. So it's 16 times 200 cubed over 12. Plus, what's the area? It's 3200. And what's H? H is the distance from the centroid, which is for the plate, to the center of the whole cross section, which is sitting on the y-axis. And yes, the y-axis of the plate is sitting on the same line as the y-axis of the whole cross section. So once again, its distance is also 0. So that term also falls away. Now people, I could have said this in the beginning, but I'm going to say it now. When there's symmetry In many cases, not all cases, in many cases, that distance there is 0. You must learn to know in which cases where it's going to be 0. Now, because the symmetry, because the symmetry on the y axis, okay, the distance is horizontally 0. If you get symmetry on the x axis, the distances on the vertical axis will be 0. You need to understand where to get it right. So, in this particular example here, the IYY, in fact, is just going to be the sum of the second moment of areas of these three sections here. So, it's going to be this plus that effectively. So, it's going to be so many millimeters to the fourth. Oh, what did I do there? An extra one. Right, so work at the answers and see what you get and check your answer against my answer. And you should have gotten 7.347 times 10 to the power 7 millimeters to the fourth. That's what you should have gotten. Okay, so 7.347 times 10 to the power 7 millimeters to the fourth. If you leave at the units, take up our answer. And the answer is not 7.347. It's 7.347 times 10 to the power 7. It's a massive number, millimeters to the fourth. And people, so that's the second moment of area about the y-axis. So we've now just answered that question over there. Next one there is just work out the section modulus about the x-axis. And if you remember correctly, we had two values on the z-axis and made two values on the ZYY. So the question only wants us to work at ZXX top and ZXX bottom. Did you get that? Not ZXX left and right. Okay. Right, so let's do that quickly. Right, people, as I said, once you work out the position of the centroid and you work at XX and IYY, as I said in my first lectures, that's really the hardest bit in the section. From here, just downhill really, because we just plug in values that we already found into the formula and get the correct answers. So let's see. So we want Z XX top is equal to I XX over Y top. Yes, that's how we called it that. Okay. So what IXX is 5.787 times 10 to the power, what did I get? 8. And what's y top? Y top is 206. And work at the answer. Let's see. Work at the answer, and we are going to get right, and you should have gotten 2.809 times 10 to the power 6. And what's the units? It is millimeters cubed. It's not the volume, it's millimeters cubed. You leave at the units, I take up a mark. Right, ZXX with respect to the bottom was fibers is equal to I XX divided by y bottom is equal to 5.787 times 10 to the power 8. That's y bottom 230.80 to 30.80 and is equal to, work at the answer yourself and you check your answer against my answer. And you should have gotten 2.507, 2.507 times 10 to the power 6 millimeters cubed. Okay, you leave at the units. It's not square, it's not millimeter, it's not millimeters to the fourth. I'll take up a mark for that. It's millimeters cubed. You leave the units out, take up a mark for that. Right, and then people, it says the least radius of gyration or R-min. Okay, and if you remember last time I said there, R-min, whenever we work at the radius of gyration, there's two possible values. There's Rx and Ryy. but we want the lesser of the two values. So R min is equal to, what's R min equal to? It's equal to the smaller of the two second moments of area. And what's the smaller value? The smaller value is it is IYY. It is IYY over the total cross-sectional area. Okay, and what's IYY? IYY is 7.347, 7.347 times 10 to the power 7 over the total. The nasty line that is. The total area, I think, was 171. Yep, was 171. 17170. Yep, so 17170. And don't forget, it's the square root of the lot, and it is equal to, like, let's see, it is 7.347 exponent 7 divided by and what did you get? I got 65.41 millimeters. 65.41 millimeters. Okay, 65.41 millimeters. It's a radius, it's a distance, so it's millimeters. If you leave the unit out, I take up a mark. So millimeters squared, that's area. So millimeters cubed, that's volume. Not it is millimeters. Okay. Now people, if I took Rxx and I divided by that, I would have got a bigger answer. But the question says determine R min. So it's the smaller of the two R values. And remember, because it's a beam, the beam is almost always stronger about the XX axis. So in almost every case, notice almost every case, it will be IYY over A, because IYY is the smaller, weaker axis. Because we said there, the IYY is normally smaller because it is less resistant to bending about the YY axis. Okay, so people there, if I flash back to my question, we've answered the whole question. Okay, I will try and work through another complex section in the next lesson, and I will see you in the next video.